Okay, thank you very much, Roberto. Hello to everybody. I'm very pleased to be here with you today. I'm Roberto Valentino. I'm Associate Professor of Geotechnical Engineering and Slope Stability at the University of Parma. The research field is mainly related to rainfall-induced shallow landslides, how to model them by using distributed physically based models. I'm going to present you today the result of the research which has been carried out in the last 3 years by the PhD candidate Giada Sannino, who is a PhD student at the University of Parma, but currently she's also employed as a researcher at the Regional Agency for Prevention, Environment and Energy of the Emilia-Romagna region. The title is Modeling the Vegetation Effect on Shallow Landslides Initiation Using Criteria 1 Dimension. I would like to start this presentation to show you this inventory map of more than 80,000 landslides that occurred in May 2023 in our region, the Emilia-Romagna region, which is located in the northern part of Italy. In May 2023, the region was struck by 2 exceptional rainfall events. The first one occurred on May 1, between 1 and 3 of May, and the rainfall was 200 millimeters in 48 hours. A second event occurred less than 2 weeks later, between 16 and 17 of May, with a higher amount of rainfall, between 200 and 250 millimeters in only 48 hours. And a lot of rainfall-induced landslides affected a wide territory. As we can see from these pictures, many landslides also affected roads and properties. We know that rainfall-induced shallow landslides could be modeled, of course, at the slope scale, but much more interesting is using distributed models. And most of these models are physically based deterministic models. We know that in the scientific literature, there are a lot of distributed physically based models. And we know that they handle this topic by different perspective, which is the inclusion of vegetation. The vegetation effect is only taken into account by very few of those distributed models. And traditionally, what we do as a geotechnical engineers is starting from a mechanical model of the slope, and we normally use to add the vegetation effect. In this study, the approach is completely different. We started from an hydrological balance model, including the vegetation effect, and we tried to add the mechanical model to this previously existing criteria model. Criteria 1D and even 3D was already published some years ago by different authors who are, of course, even co-authors of this research. Criteria takes into account the hydrological water balance in one direction based on Richard's equation. It takes into account Van Genuchten-Moellem model for soil water characteristic curves. Also, hydraulic conductivity function is taken into account because the shallow part of the soil is for most of the time in partially saturated conditions. The model is also able to take into account evapotranspiration, crop development, snow melt, solar radiation. Moreover, the model has the possibility to take into account a layered soil with different layers of different thickness. So normally the criteria model had as input data, daily meteorological data, soil hydrological parameters, plus vegetation parameters. In the original version of the model, the only output were volumetric water content and soil suction. But in this study, we tried to add another output, which is the factor of safety of the slopes. The model of vegetation is taken into account mainly into two components. The first one is the root density changing with depth, which takes into account the shape of the root systems that change according to the different plants, and the secondary, the canopy development over time, which is based on meteorological data. In this slide, we can see an example of the characteristic of the parameters which are strictly related to the plants. First of all, we have the evapotranspiration, we have transpiration, evaporation, and the leaf area index. And in a 1 year span, we can see that it follows normally the seasonal trend. As regards the slope stability model, we used that introduced by Lu and God in 2008. It takes into account different soil parameters like effective soil cohesion and the root mechanical contribution, but in this case, as a CR, we consider only the mechanical contribution of roots, disregarding the hydrological effect of roots. Then we consider the actual soil water content, the residual and saturated water content, soil friction angle, of course the slope angle, the depth of interest, and the unit weight of the shallow part of the soil. Of course, this model is based on the limit equilibrium method, and it considers the sketch and the scheme of the infinite slope. The Lu and God model is based on the definition of the so-called suction stress, sigma S, which is a function of soil suction and the volumetric water content of the soil. It was needed to test and to validate the model, and we validated the model by applying the same model to the test site at Montuè. Montuè is located in Oltrepo Pavese, which is in the northern Italian Apennine. We selected the specific site where the slope was subjected to landslides in April 2009, and in this map on the right side of the slide, we can see the shape of the landslides which occurred in April 27 and 28 April 2009. They are colored in orange. We installed on the same slope a monitoring station which corresponds to this orange star here. And during the monitoring period, and we installed this station in March 2012, and during the monitoring period, which is still ongoing, and specifically on the 1st of March and between the 1st and 2nd of March 2014, a shell of landslides occurred very close to the position of the monitoring station, which is colored in red in this map. The monitoring station is composed by a thermohygrometer, a photovoltaic panel, a net radiometer, an anemometer, a rain gauge, and of course all these data are collected by a data logger. In the soil, we installed different kinds of devices in order to acquire measurements of water content at different depths, and even soil suctions at 3 depths, specifically soil suction at 20 centimeters, 60 centimeters, and 1.2 meters. The soil, in this case, is mainly a silty soil. This is a photo of the landslides that occurred in the between 1st and 2 of March 2014. Here we can see the meteorological data in a time span between 2012 and 2015. These are 4 years of rainfall data and the temperature data. And this time span has been selected in order to take into account the landslide event of the 1st of March to 2014. This event was characterized by 60 millimeters of rainfall in 24 hours. But we can see how the cumulated rainfall was much higher because of the previous rainfall. In this slide, we can see the results of criteria, one dimension, in terms of soil water content at different depths. On the left side, we can see the field data, which are represented in dot black line, and we can see the result of the model by considering bare soil, it means without vegetation in red, and considering vegetation effects in green. This first result on the left side of the slide corresponds to the depth of 20 centimeters. Of course, there is also the daily rainfall in the time span of 4 years. On the right side, we can see the same result at 40 centimeters of depth. And we can see very clearly how the vegetation effect allows the model to be much more close to the experimental field measurements. Instead, considering only bare results gives worse results. Here we have the similar results at 60 centimeters of depth and 100 centimeters of depth. And again, we can observe, of course, the change of water content due to rainfalls and due to season, and we can identify the wet season in the winter with respect to the dry season in the summer, and we can see again how the vegetation effects is gives much more reliable results with respect to the bare soil. Here we have the similar results at 1.2 meters and 1.4 meters, and we have the same similar results. We also show the results of criteria-1D in terms of soil suction at the 3 depths. At 20 centimeters here, we can see that even in this case, we have, considering vegetation, we have an overestimation of suction during the dry season, but generally speaking, even in this case, the vegetation effect allows to obtain much better results at 20 centimeters, the same at 60 centimeters. And we can see that in this case, at 60 centimeters, the vegetation effect is much more useful with respect to the bare soil. And the same conclusion is related to the soil suction at 120 centimeters of depth. At this depth, we see how the vegetation effect is much better than considering the bare soil. Of course, after validation, in terms of water content and soil suction, we obtained the trend of the safety factor of this slope. On the left side, considering the bare soil, on the right side, considering the vegetation effect. In both cases, we can see as a different scale of gray colors the safety factor at different depths. On the left side, we can see how the bare soil, of course, it correctly predicts the safety factor less than 1 in correspondence of the landslide occurrence, but we have also a false positive in another date before the occurrence of the real landslides at 1 meter of depth, which was also the real observed depth of the real landslides. Instead, on the right side of the slide, we can see that considering the effect of vegetation instead of bare soil, that false positive is avoided, and the model allows to predict the landslide occurrence exactly in the same day of the real landslide. So we can conclude saying that the implementation of a slope stability model in an agrohydrological modeling scheme has demonstrated a valid tool for rainfall-induced shallow landslide prediction. The possibility of dynamically modeling the transpiration-induced hydrological effects is of importance for this kind of landslides. The use of a soil water retention curve without any hysteretic effect and the underlying assumption of homogeneous soil layers sometimes may not be appropriate. However, in this case at the Montois test site, thanks to the possibility of modeling vegetation dynamically during time, the choice of using texture-based values of the saturated permeability of the soil showed its efficacy. Moreover, the root density distribution and the presence and even the life of plants affects, of course, soil suction. We can say that disregarding this component in physically based deterministic models can lead to overestimation. It means a false positive of landslide events detection. Moreover, the pre-wetting condition due to the evapotranspiration-induced hydrological effect has an important impact on slope stability evaluation. The triggering models for shallow landslides should take into account that plant transpiration can become even nil when the soil reaches saturated conditions. Accounting for this mechanism can improve the accuracy of models. The results of this research, at least in one dimension, has been already published, recently published on Landslides journal. But after the publication of this paper, there was a development. So Criteria-1D is becoming Criteria-3D. So I would like to add some preliminary results showing the same test site of Montois and showing different 3D maps of this case water potential of the slope at Montois test site with DEM resolution of 1 meter with water potential at 1 meter of depth. On the left side, we see at the 5 EM on 1st March 2014, but following this rainfall event, of course, the water potential changed 24 hours later. Sorry, it is not visible as the map, but the values on the color scale here and here are different, so the difference is there. Much more visible is the difference between the situation before the landslide event and after the landslide event in terms of water content at 1 meter of depth. Before the event, we can see on the left side. After the event, on the right side, we can see in correspondence of the green dots. This is the location of the real landslides. Of course, the saturation increases and the volumetric water content is increasing towards completely saturated soil. The safety factor evaluated at 1 meter of depth before the landslide is on the left side of this picture. This is at the 5 EM on the 1st of March 2014, and we see how the safety factor is still higher than 1, but after rainfall, in the same position of the real landslide, the safety factor drops below the value of 1. This is the result of the safety factor at 1 meter of depth, but I would like to show you even another result at 30 centimeters of depth. Before the landslide, the big landslide, the observed landslide, we have this kind of result. and after the rainfall event, we have this result. Could I have a question for myself, for the research group, but even for you? Would it be possible to consider this as modeling of erosion? If yes, I thought in this case, most probably the erosion effect is overestimated with respect to the real erosion effect, but at least we can say that we have at our disposal only one model in a 3-dimension, which is able to take into account both phenomena. More shallow phenomena, which are more related to erosion, and even a more deep phenomenon, which is more related to a rainfall-induced shallow landslides. And we know how it is rather rare to find modeling erosion by using physically based models. So this is a perspective for the future, and of course we need to validate even in this kind of model. Another added value of the CRITERIA-1D and 3D model is that it is completely open source, so everyone can access very freely to the model. The model has been mainly developed by the regional agency for prevention prevention, environment and energy of the Emilia-Romagna region. But of course, this research is the result of the cooperation between different research groups at the University of Parma, which is my university, University of Bologna, and University of Pavia, under the co-funding coming from the European Union. Thank you very much for your kind attention, and if there is any question, I am available.